Hi, grade 12s. We're here to do physical sciences, and the topic for today is work, power, and energy. Work, energy, and power is what we've called it. Now, guys, this is a really important section of mechanics, paper 1, and you should be looking forward to it. It's something that shouldn't be giving you nightmares, because if you study hard and you follow the basic principles, you can do well in this section. So don't let any preconceived ideas get to you that this is difficult, because if you've just learned your basics and you apply them, you will be doing fine. So let's go through what you need to know and what you need to find out. So make sure you're able, first of all, to be able to tackle these problems. You need to be able to define what work is and apply the definitions to problems. And we'll be doing quite a bit of that. Then the next thing that I would like you to do, to make absolutely sure that you can manage the section and master the section, you need to revise the drawing of free body diagrams, and in particular, you need to be able to find components of forces. Don't be scared of components either. It's something that is very useful. It's a technique that we will use quite often. Then you should be able to state and apply the Work-Energy Theorem. This is a wonderful theorem, and it's something that will help us do lots of calculations, but you do need to understand it very carefully. So the next part of it is you also need to understand, when you're dealing with energy, Work-Energy Theorem, the other bit of theory that you need to know is the conservation of mechanical energy. So you need to be able to state it as well as apply it. Remember what energy is. This is a very interesting topic. And being able to recognize that in a system, normally, under normal situations, we do not create or lose any energy. We do need to recognize, though, that there are things when energy is conserved and when energy or mechanical energy is not conserved. So there are conditions when we recognize, absolutely, mechanical energy is conserved. But there are times, particularly when we have this head that raises itself, called a non-conservative force. When there are non-conservative forces involved, then mechanical energy is not conserved. Overall, energy is conserved, but mechanical energy isn't. So what are these non-conservative forces? The one that you are supposing to deal with and most likely to deal with is the one called friction. So it's the work done by friction. Okay? And as something is happening, energy is used up in overcoming friction, and we find that that energy is transferred or converted into other forms of heat and sound, and sometimes even light. So we need to be able to recognize that. Next part, define power. Work, energy, and power, they're all interrelated, and you'll see that the questions aren't asked separately. You need to know this as one unit, and it links very nicely to Newton's laws and to forces and even to momentum and impulse. So you've got to be very awake when you're dealing with these. So define power. You need to be able to calculate power when work is done, and you need to also be aware of this equation, that the average power is equal to the force times of the average velocity. This is particularly used when we're pumping things or things are moving, and they're usually moving at a constant velocity. It's not the only formula, but you do need to be able to use it and know when to use it. Don't just use it at any odd stage. Right, I think I've recapped quite sufficiently, and the best way to get in and understand a little bit more about work is to look at some exam questions. So here are some exam questions. First one is taken from the February paper of 2014, paper 1, and it's question 5. If you're wanting to revise work type questions, you can look at all the previous exam papers, and those that were previously written for NCS, so from 2008 onwards, question 5 is probably when you're going to find it. We're not exactly sure what question number it will appear in this year's exam, but you will need to be able to practice and apply all of these things. Nothing much has changed as far as this topic is concerned for the CAPS exam. So go and do as many as you can. Read the memos. Make sure your setting out is very accurate. Do not get confused. Make sure you read the memo and write things down exactly as they're saying. If you're having a problem, either ask your teacher or send us a question at the help desk. So let's move on. Read the question. Select the information we need. We're told a loaded truck has a mass of 5,000 kilograms and it travels up a straight incline at a constant velocity. Very important that we recognize that velocity is constant, 15 meters per second. It's going quite quickly at 15 meters per second. At the top of the incline, the truck is at a height of 55 meters above its starting point. The work done by frictional forces is 8,5 times 10 to the 4 joules. Now remember that that work is non-conservative. It's negative work. It's going to be taking away from the total mechanical energy, and we'll need to apply that. We can ignore the rotational effects of the wheels of the truck. Now, so when they say ignore, we're just going to ignore it totally. It might make a difference if we were doing the calculations, including the rotation. We don't have to cover that at grade 12 level. So the first question, straightforward, is we need to define power, but in words. So what we're going to say is power is the rate at which work is done. There is an alternative definition, which I like, which says that power is the rate at which energy is transferred. And that's a very interesting connection between work and energy. So be aware of that. If we're transferring energy as the body is moving and it's increasing its kinetic energy, losing its potential energy, energy is being transferred to it. And power is the rate at which that transfer takes place. Rate means we divide by time. So the formula that you're going to, or the equation we're going to look on the data sheet, it's just going to be the work over the time that change has taken place. Energy transfer. Okay, now the next part of the question, which is really fundamental. In any of these mechanics questions, you need to be able to draw diagrams, and we need to recall identifying how forces are involved in work and in power. So here we've given a free body diagram showing all the forces acting on the truck as it moves up the incline. So I'm going to recognize free body diagram. Recognize that the slope, although we're not going to put it in, is in that direction. Okay, I've drawn it in, but I'm going to take it out in a minute. So we recognize that's where the slope is. Perhaps I should just change the color of that as well, just so that we've got it as a different color. I'd prefer it to be even the white would be better. So let's just put it in as a white line. We can remove it. The reason I've put that in is so that we can get the angles more or less correct. So a truck sitting on a slope, what do we know about it? Well, we know that there's a force that pulls directly downwards. And that force is the force of the earth acting on the truck. And I'm going to put that in as a downward force straight downwards. Now, you can label it as Fg, or you can say that it's equal to the weight. We just need to recognize that's mg. It's the mass of the truck multiplied by the acceleration due to gravity. Next thing that we know is that there's always a contact force, the force of the surface pushing up on the truck. So if the truck is on an incline, that surface where the wheels are pushing down, the surface pushes back at 90 degrees. So we're going to draw that in as the normal force. So at 90 degrees to this incline, we've got the normal force acting on, put it down as normal. We're going to make sure that you not only draw the diagram, you're going to need to give a key as well to say what those forces are. Now, the next thing we recognize, the truck is moving up the slope. Now, it's not just going to go up by itself. So there is an applied force that the engine of the truck is pushing the truck up. So this is the force of the engine. Now, very, very important. We were told that the force of the truck and the force of the gravitational is in place. There's also a frictional force. So what we need to recognize in our next statement is that there's a frictional force. And I'm going to put that frictional force in, and I'm going to put it in acting in the opposite direction to the motion. So truck is moving up, the frictional force is acting against it, but we don't know at this point, other than the fact that all of these forces are going to give us a net resultant up the slope. There's a net resultant up the slope combined because we know that it's moving at constant velocity. But let's not get too carried away with that statement at the moment. We're just going to label this as the frictional force, FF, or just a little f like that. So let's just make sure that we've got all of these. We're going to say N is the normal force. Fg is the force of the Earth. We also recognize that we've got the force of the engine. It's the force of the engine, and that's acting on the body of the truck. And then we've got the force of friction, and that's friction. Now, guys, we're going to refer to this diagram quite often, and you need to make sure that you understand how to draw these. Remember, you don't need to have that line in. I was just putting it there so we get the slope correct. But once you've got the frictional force and the engine's force, you can actually just erase it or take it away, or not even put it in. It was just to try and explain it for you. So there's the free body diagram. Let's move on to the next part of the question. Use the work-energy theorem to calculate the work done by the engine of the truck to get it to the top of the incline. So there's the truck, and it needs to get up there. It's going at a constant velocity. We need to apply the work-energy theorem. So what does the work-energy theorem say? Let's write it down as a formula so that we've got it, or an equation. We're going to say work net is equal to the change in kinetic energy. Change in kinetic energy means the kinetic energy of the final minus kinetic energy of the initial. But remember that immediately we know that the velocity was constant. So there's no change in kinetic energy, and I can say that the work net for this situation is 0. And that's very important that we've got that understanding. But what are we asked to do? We're asked to find the work done by the truck. So work net, we need to define what work is. And remember that work net is equal to the net force, or the resultant force, times the change in position times cos theta. What we're going to need to do is to break this apart into work net is done by the work done by the individual forces. The force of the engine plus the force of friction plus the force of gravity. Now remember, this engine had to lift the whole truck. Look at it. The truck was at the bottom over here and it's now 55 meters. The force of gravity is pulling the truck down. What we need to recognize is that the work done by gravity or against gravity is conservative. But the work done by friction is non-conservative. So we will recognize that that has an overall effect. Let's add to this now and let's break the equation apart. We're going to say we want to find Fw plus the frictional force, the work done by friction, plus the work done against gravity. We're going to say that all of that's equal to 0. We'll put in the values that we've got, because remember we were told that the work done against the frictional forces is 8,5 times 10 to the 4 joules. But that's negative work. We can put it in as a negative. So I'm going to put in negative 8,5 times 10 to the 4. Plus, what's the work done against gravity? Well, we know the mass of the truck is 5,000. Remember, work, 5,000 newtons. Work, we had it up there, is F times delta Y, in this case, times cos theta. And what was the force? The force, we were told, is equal to the weight. And we know that it's a 5,000 kilogram truck, and that's going to give us mg. So we're going to say 5,000 times 9,8 times the distance. The distance, which is over here, the height that it's being lifted to, 55, times cos theta. Now, guys, here is the important thing. In which way was the truck moving vertically? Hope you've got it. The truck moved up. Which way was the force of gravity? It's in the opposite direction. It's downwards. So what's the angle between the upward force, which is where it got to, it moved up, and the downward force? What's the angle between those? Hope you can see that it's 180 degrees. So we're going to put it in as 180 degrees here. Now, we recognize all of that is equal to 0. Let's do the calculation. Pull out the calculator, and we can now start to substitute things in. We're going to start with the calculation of the work done against gravity. 5,000 times 9,8 times 55, which was the height, times cos of 180. Now, you should know, having done these a few times, that that's going to give you a negative answer. And it is negative 5,000, sorry. Now, what we've got to do is we've got to add in the negative value of the friction. So it's 8,5 exponent 4. So 10 to the power of 4, and that will give me a negative answer at this point. So I've got the equation Fw minus 278, and then there are 4 zeros there. I hope you can see 1, 2, 3, 4 equals 0. Well, that's not difficult now. We can just therefore say that the work done by the engine, the force applied, is going to be 2,78, and we put it in scientific notation, and we'll get times 10 to the 6. There are 4 zeros and another 2 for the 78, times 10 to the 6, and the units are joules. Okay, so this truck had to work quite hard because it had overcome gravity, it had to overcome friction, but it eventually got there. And it was doing it at constant velocity. Hope you've understood how we apply the work-energy theorem. Let's move on to the next question. it then says to us, calculate the average power delivered by the engine of the truck if the truck takes 60 seconds to reach the top of the incline. So power is equal to the work done, and it was average because it was net over the time. And so all we're going to do is we're going to substitute that value, 2,67 times 10 to the 6, and divide that by the 60 seconds. So if we put that, get our calculator out, let's just make sure that we multiply that by -1, so we get the right value, and we're going to then divide it by 60. And the real reason I think the examiners like this sort of question is because they want you to manipulate from scientific notation to normal notation, and they want to make sure that you understand that the units of energy and work are in joules, but the units of power are in watts. And sometimes that can be confusing because we've got W's all over the place. So this will be 4,63. Now, if we're changing to scientific notation, then you're going to write that as times 10 and count the number 1, 2, 3 threes, 4. So it's going to be times 10 to the 4 with the 6. And that needs to be in watts. Okay. So it's 4,36 times 10 to the 4 watts. Very good. Guys, see if there's one last part of the question, and there is. It says to us, how will the work done by the engine of the truck compare? Okay, wait a minute. We missed out a bit. The truck returns down the same incline at the constant velocity. This diagram is the wrong diagram, but basically what we're saying, the truck moves downwards. It's gone up and now it goes downwards. And it's going at the same velocity of 15 meters per second. How will the work done by the engine compare on reaching the bottom compared to our calculation when it moved up? And what you have to do is you have to write greater than, smaller than, or equal to, and give a reason for your answer. So think about it. Is the truck going to do more or less work, or is it going to do the same amount of work? Well, guys, it's going to do a smaller amount. And the reason is simply this, that the engine of the truck is going to apply a force downwards, or let's just put the force of the engine is going to be downwards. But what's also going downwards? It's the force of gravity. Fg is now going to be assisting the truck. So instead of that cos 180 giving you a negative value, it's going to give you a positive value. And so what we can answer is that the gravitational force does positive work. And so that means the engine's got to do less, which means engine does less. Okay, guys, I know this has been an intense question, but hopefully you're starting to get confident about doing these. Follow the basic steps, but for the moment, let's take a little break. Welcome back from that little break. Let's get into our next question straight away. So question number 2 says, we have a simplified diagram below of a slide and a boy and a girl. The slide is 3 meters. It's 1,5 meters high. The boy has a mass of 40 kilograms. The girl has a mass of 22 kilograms. The girl accelerates uniformly from rest down the slide. She experienced a constant frictional force of 1,9 meters. The boy falls vertically. He just decides to take a jump from the top of the slide through the height PR. So from that position to that position, he goes straight down 1,5 meters. We're told to ignore the effects of air friction. So the first question, the theory question, write down the principle of conservation of mechanical energy. And what we're going to say is that mechanical energy in a closed system or isolated system is conserved, is constant. Okay? So it doesn't change. What it is at any point, it will be the same of that system. Now, please don't get confused if they're doing different things. We look at an object within a system and we're going to say at any point, like a ball being dropped, at any point it has the same mechanical energy. Now, the next part, we've done these before, the drawing of free body diagrams to show all the forces acting. Now, the boy, while he's falling vertically, what sort of forces? We're told to ignore air friction. All we're going to have is the force due to gravity that's acting downward. What about the girl? Well, remember, she's sliding down. So yes, there is the force due to gravity, but we also recognize that there is the force of friction and there's the normal force. And so we have those. You would go and label each of those in the exam to make sure that your examiner knows exactly what you're talking about. But we want to move on to get to the real meaty stuff. It now says to us that what we're required to do is to use the principle of conservation of mechanical energy to calculate the speed of the boy when he reaches the ground. Now, when it says use mechanical energy, that doesn't mean you can use projectile motion equations of motion. No, we have to use mechanical energy. So, conservation of mechanical energy. What we're going to say is that the mechanical energy of the boy is equal to his kinetic energy plus his potential energy. And we know that that has to stay the same. So what I'm going to say is the following. We're going to say the kinetic energy, or the mechanical energy, EK, at any point, plus the potential energy at any point. And the point that we're taking here is at the top of the slide. The top is going to be equal to the mechanical, the kinetic energy at the bottom plus the potential energy at the bottom. So we're just labeling it so we've got it very clear that that's the case. Now, what do we know about the the kinetic energy of the boy? We know that that's half mv squared, and at the top of the slide, the velocity was 0. So I'm going to substitute 0 in there. Now, what about the potential energy? Remember, potential energy, I'm just going to do it on the side here so you've got an idea. It's mgh. So potential energy mgh, kinetic energy ek is equal to half mv squared. We're going to use those to substitute in. I'm going to do my substitution now, and I'm going to say we know the boy had a mass of 40 kilograms. There it is. And he was a height of 1,5 meters above the ground. So it's 40 kilograms times 9,8 times 1,5. And that will give me my total mechanical energy before the boy moves down the slope. This is what he's got at the beginning. And in fact, it's what he's got all the way through. So what we can say, that has to be equal to his kinetic energy at the bottom, which is going to be half, times his mass. Now I'm putting his mass as 40, times his velocity squared. Now, what about his potential energy? Well, what's his height above the ground when he hits the ground? It's 0. We could put in his mass. Yes, we can put in 9,8, and we can put in 0, just to show that we've substituted correctly. So what we're recognizing here is the importance of substitution. Now, what's the unknown? It's the v squared. Let's get this all into a calculator, and let's see if we can find v squared. So clear the calculator from the previous activity, previous exercise, and we are going to simplify it. I'll go a little bit slower than just doing it all in one step. 40 times 9,8 times 1,5, and we're going to say that that is 588. Now, what's that going to be equal to? That's equal to half of 40 is 20 v squared plus, now, on this side, 40 times 9,8 times 0, we know that's 0. Okay? Don't have to even use the calculator for that. So where am I going to go next? Well, I want to get v squared on its own. So v squared is 588 divided by 20, and I am going to need the calculator to do that because I don't do square roots in my head unless they're perfect squares. So there we go. This one isn't. It's 29,4. So please remember this is 29,4, but it is v squared. You must square root to find the value of v. So we're going to say square root, put the answer back, and take the square root of the answer, gives it to you as a surd, but we want it as a decimal, which is 5,422 meters per second. And let's just check what they asked. It just asked for the speed. So we don't have to worry about direction. We just can say it's 5,42 meters per second. We know it's downwards. Yes, that's the speed of the boy when he hits the ground. Okay, moving on. Next part of the question. Now it says, similar to question that we did earlier, use the work-energy theorem to calculate the speed of the girl when she reaches point Q at the bottom of the slide. So remember what the work-energy theorem said. It said that the work net is equal to the change in kinetic energy. And the change in kinetic energy is going to be the kinetic energy final minus the kinetic energy initial. We are going to need to substitute things in then to get this whole story sorted out. So what components or what parts of work net do we need to get? Well, let's just try and simplify first of all, working from left to right. We can say that the work net is going to compose of two aspects. It's going to compose of the work done by the force of gravity, force due to gravity. If we go back to the diagram that we drew, remember there is the one force. And that's why these force diagrams are so useful. There is the other one. Both of those have an impact on the work done by the girl. Now you might say, well, what about the normal? Well, it's at 90 degrees. And a cos of 90 is 0, so we don't even include it because it's not going to give us work in that respect. So if we go back here, this means that we're going to need to calculate the work G plus the work of friction. And here we're going to do and say the final kinetic energy, which is going to be half, put that back, just give this half mv squared, and that's the final velocity, minus half mv squared, the initial velocity. What do we know about the initial velocity? It's 0. So when we come to substitute, we can call that to be 0, and we'll be fine in terms of that. The thing I want to look at a little bit more carefully is the work component, the left-hand side of this equation. So if I'm going to the left-hand side, what do I know? I've got the mass times g times cos theta. And what about the force of friction? Well, in that case, it's the frictional force, which was given, times, and I've left out a delta here, delta y, and I've left out over here, I've got force times the delta x, because it's going down, and I'm going to actually make that an x as well, times cos theta. I'll explain exactly why I'm doing that. So as she's moving down the side, all the time gravity is acting on her. But what do you notice? The change in position is in that direction. We don't want the component in this case. There's another way of doing it. What we'd like to be able to do is to say, if the displacement, the change in position from P to Q is in that direction, well, what's the direction of the force? The force of gravity is straight downwards. Well, this angle here, notice, it's part of a 90-degree triangle. That angle is an angle of 60 degrees. So for all the time it's moving down, the angle is 60 degrees. So I'm going to put that in and recognize it's the distance down the slide. So what was the mass of the girl? Let's get that right. The mass of the girl was 22. So it's 22 times 9,8. What was the distance? 3 cos 60 degrees. Plus, what was the frictional force? They gave it to us. There it is, 1,9 newtons. Now, notice I put the 1,9 in, put it in brackets so you can showing that it's all nice and neat, 3 meters. Now, guys, here's the important thing. What about the cos theta? The frictional force was upwards. The girl was going downwards. Can you see? That's at opposite angles. What's opposite? Cos 180. And remember, all of that has to be equal to half mv final squared. And in fact, let me just substitute the value of her mass in, half times 22 v final squared. Wow, that's quite a bit to do. So let's get the old calculator out and we can make sure that we get all of this detail sorted out. So the first part I'm going to do is the work done against the frictional, not frictional, against the weight, the force of gravity. So I'm going to say 22 times 9,8 times 3 times cos of 60 degrees. Now, remember I showed you the triangle. You've got the slope, the bottom angle is 30, the top angle must be 60 because it's a 90-degree triangle. Make sure you don't get confused about the angles. This gives us 323,4 joules at the moment, plus the next part is the work done against friction. Now, let's pull that detail in and get the calculator up. I'm going to clear that part, and I'm going to do 1,9, because that was the frictional force, multiplied by 3, multiplied by cos 180. The cos 180 will take care of the direction. So we get this being a negative 5,7. So the value here, negative 5,7, and that's all equal to 11 times V final squared. So where do we go? Let's add it all together and let's simplify it, and we get that answer plus 323,4 equals, and then let's divide that whole thing by 11, and that will give me this answer of 20. So V squared, V final squared, is 28,88. But that's V final squared. I don't want the square. I want just the V. So what am I going to do? Yes, I'm going to square root. So I'm going to take the square root, put in my answer, and I get an answer of 5,37 meters per second. Okay, 5,37 meters per second. Hope you can see that friction has an effect. But let's take a look at what the next question is. And it says, how would the velocity of the girl compared to the boy at R. So if the slide has no friction. So if we look at it with friction, you can see that the boy had a velocity, if we look back at our answers, of 5,42. This was with friction. This was just falling. 5,42, this is the boy. The girl with friction was 5,37. Now, meters per second. Now they say, what would happen if there was no friction? If we ignored the frictional force? And in fact, what can we say? Well, the forces would be equal, because the only force, the only work that is being done is the work due to gravity. And work due to gravity is going to produce the same speed, because acceleration due to gravity is constant and independent of mass. Doesn't matter that the boy was particularly heavier than the girl, but they're going to be equal. You didn't have to give a reason. In this case, you just had to say. But please remember that that is a fact. Okay, time for another little break, and we'll be back for our last question. Guys, welcome back from that little break. We've got one last question, and hopefully we can get through it in the short time left. Let's get to it straight away. You'll see that it's quite similar to some of the other questions we've done. We've got a box, crate, that's 5 kilograms. It's moving down the path from X to Y to Z. It's not drawn to scale. This initial part is frictionless, but this part over here, there is a force of friction. So what we will need to go to is, let's have a look at the first question. We were asked to apply the principle of conservation of mechanical energy to calculate the speed of the crate when it reaches point Y. So just between X and Y, and what we're going to recognize is EP at X plus EK at X is equal to, X is equal to EP at Y plus EK at Y. Now, I'm not going to waste too much time on this because we've done one quite similar. Please remember to substitute your values in. So you're going to have to remember and write down what they are. mgh at X plus half mv squared, that's at X, is equal to mgh at Y plus half mv squared at Y. So this one is X and Y, and we simply substitute the values in. 5 kilograms was the mass, 9,8 is the acceleration due to gravity. The height at X was at 5 meters, plus half times the mass times the velocity, and we know the velocity at the initial point at X was 0, and we're then going to substitute the mass in over here, which is 5 kilograms times 9,8. The height at this point is 1 plus half times the mass, again, is 5 times the velocity squared, and that's the one that we're trying to find. Now, guys, at that point, the physics is done. You've stated it, you've substituted it, and you simply need to use the calculator, but please remember to find the square root, because that's velocity squared. But if you do it, you'll find that the velocity at this point, at velocity y, at point y, is 8,85 meters per second. And that's very important that you practice that substitute. Become familiar with your calculator so that you can get it right. Of course, if you're using a Casio calculator, it's so much easier. Next point. We're now asked some more interesting questions that allow us to question the physics and the principles of physics. It then tells us that on reaching point Y, the crate continues to move down YZ of the path. It experiences an average frictional force of 10 newtons. So remember, there's a frictional force of 10 newtons, and that frictional force is acting upwards. The initial velocity at point Y was 8,85 meters per second. So it experiences that, and it reaches point Z over here with a speed of 4 meters per second. That's what its speed is at point Z, 4 meters per second. So clearly, as it's been moving down, even though it's accelerating because the gravitational force is pulling it down, now the frictional component has slowed it down quite significantly because it was much faster. It hasn't increased in speed. It has a negative acceleration for this section. So what they're asking is, apart from friction, write down the names of 2 other forces that act on the crate while it is in this section, YZ. Well, there were forces that were acting there. They haven't gone away. What is the one force? Well, clearly we know it's the weight of the object, or it's the force due to the attraction of the Earth. Okay? The second force, which is often not used, but it does have relevance for friction, is the normal force. Because remember, the frictional force can be calculated using the component of the normal force and the coefficient of static friction or kinetic friction. If it's moving, it's kinetic friction. Static would be if it was stationary. So those are 2 important forces that we need to write down. So we would say the force Fg is the weight of the object, and N, which is the normal force. The force of the surface pushing up on the crate. Now, in which direction does the net force act on the crate as it moves down the section YZ? And write down only Y to Z or Z to Y. Okay, so we want the direction. Is it going downwards, Y to Z, or is it going upwards? Well, we've got to see what's happened. What's the net result? Please remember, this is not just the force of friction. It's not asking you about, it's saying the net. In this case, the net happens to be the force of friction, is bigger, but it's not only that. It's because the frictional force is so large that it's overcoming the force of gravity, or the force due to gravity. So what we recognize is the force acting from Y to Z or Z to Y. Well, clearly it's the net force. Look at the change. It went from a velocity of 8,85 to 4. That means it's slowed down. Because it's slowed down, the net force must be from Z to Y. Now, the last question, or the second to last question at least, is this one where we have to use the work-energy theorem again. But it asks us a different question. It asks us to calculate the length of YZ. Now, let's just put the statement down, and even if we've got to rush through the calculation, I want to just highlight some important points. We recognize W net is the change in kinetic energy, and what we're going to recognize that W net is made up of a part of the weight of the, in other words, due to gravity, and then it's also made up of the force of friction, and we're going to look at the change in kinetic energy. I'm going to write it as half m, and then say V final squared minus V initial squared. And those final and initials are really at y and z. So remember, it ends up down at the bottom at z. So that's at position z, and this is at position y, and we know what those are. So clearly, what we're going to need to do is to do some calculation in terms of distance. Now, that's not a problem. We can simply put these into the equation and recognize that this is half times 5, and the velocity was given as 4 meters per second squared, and the initial velocity, we calculated this as 8,85 meters per second. We must square that, and we're going to subtract that. Now, what about the weight story and the other aspects here? Please notice that what's happened to the effect of the gravitational force. It's moved the object, the crate, from that position to that position through a vertical distance of 1 meter. And that vertical distance is in the same direction. So what we're going to say is the force is the mass times the acceleration due to gravity. The distance is 1, and in this case the cos theta is going to be 0 because they're in the same direction. Plus, what about the frictional force now? The frictional force is acting in the opposite direction to the direction of motion. So let's just fill that in. We know what the frictional force, it was 10. We know that the distance is what we want to find, delta x. What about the angle? Well, you know it. It's cos 180 degrees. Now, guys, that all looks a little bit messy, but we can simplify it a little bit. And if we do this on our calculator, we will find that delta x turns out to be 20,48 meters. 20,48 meters. I'm going to leave you the task, punching in the numbers on the calculator, and you can check your answer. The final part of this question is to say, how will the velocity of this 10 kg crate at y compare to a 5 kg at y? So if instead of how will the velocity of a 5 kg, another crate, 10 kg, moves down from y, from x to y, remember that's frictionless. So what do we know about the velocities? Well, they're going to be equal. How do we know? Well, because there is only the effect of the acceleration due to gravity, okay? And mass doesn't influence that. So that wraps up our section today on work, energy, power. Hope you've enjoyed it, and study hard. We'll see you again soon.